Good afternoon, and welcome to the second of two videos regarding section 12.4 in your textbook, Limits at Infinity. So, in this video, we're going to cover a couple of things. The first of which is limits at infinity for rational functions. Now, hopefully you recall that a rational function is simply a function that's got both a numerator and a denominator. And so, um, in this case, let's consider the rational function f of x equals n of x divided by d of x. N stands for the numerator, d stands for the denominator. And we'll define n of x as equal to a sub n times x to the nth power plus all the way down to n equals 0. And so a sub 0. All right. Now, this could be this could be, for example, 2x squared plus 2x plus 2. Okay. So in this case, the value of a would be 2. The value of n, at least for the first one, is x to the 2th power, x to the first power, x to the 0 power, and so on. And the same thing is true for b sub m times x to the m power, all the way down to b sub 0. All right. So if the limit of f of x as x approaches infinity is as follows, all right, then the limit will be equal to 0 if the value of n is less than the value of m. In other words, the numerator will end up being a smaller number than the denominator. It will be equal to a sub n over b sub m if n and m are equal to one another. And finally, if the value of n is greater than m, then the limit will not exist because it will be approaching infinity. All right. If you think about this, if you've got a numerator of n over m as they're approaching infinity, if n is a small number and m is a bigger number, then we're going to get closer and closer to 0. All right. If a sub n over b sub m, if n equals m, then they're going to be approached whatever this ratio is of the coefficients, 2 over 3 or 3 over 7 or whatever it happens to be. But if n is much greater than the value of m, then the limit is going to be getting bigger and bigger and bigger, or smaller and smaller and smaller, depending on whether we're approaching positive or negative infinity. And since they're approaching two different numbers, the limit does not exist. All right. And so that's the idea for limits at infinity for rational functions. As always, it's probably helpful to look at an example. So let's do that, shall we? All right. So example number 3. You are manufacturing greeting cards that cost 50 cents per card to produce. Okay, seems simple enough. Your initial investment is $5,000. Which implies that the total cost of producing X amount of cards is given by the equation C for cost is equal to 0.50x plus 5,000, right? That initial $5,000 investment plus 50 cents per card. Now, the average cost per card is given by, and the average cost per card is going to be C with the little symbol over it, and that's going to be C divided by X, the cost divided by the number of cards that you produce. And so therefore, that's going to equal 0.50x plus 5,000, all divided by X, all right, the number of cards that are produced. So the question asks you, let me go back, to find the average cost per card when the value of X is equal to 1,000, when the value of X is equal to 10,000, and when the value of X is equal to 100,000. And then finally, part D of example number 3 asks you to find the limit of the total cost as x approaches infinity. In other words, as you produce an infinite number of cards, what is the limit of the cost per card? Okay, so how do we do this kind of thing? Well, we know that the total cost is going to equal the cost per card, which is going to equal 0.50x plus 5,000, all divided by x. And so in this case, all we got to do here is plug in our numbers. So C, if we have 1,000 cards, is going to be 0.50 times 1,000 plus 5,000, all divided by 1,000. And if you do a quick bit of math here, half of 1,000 is 500. That plus 5,000 is 5,500. Divided by 1,000 is going to give me a grand total of $5. That's a dollar sign and 50 cents. Okay, so that's going to be my cost per card. All right, so it's not very economical there. Now, if I produced 10,000 cards in this batch, then 0.50 times 10,000 plus 5,000 all over 1,000. Now, 1/2 times 10,000 is 5,000, plus 5,000 is 10,000, divided by 1,000 in this case is going to be $1. $1.00. All right, so it's getting cheaper. All right, the more cards I produce, the cheaper it is to produce each individual card. Now, if I try to do this with 100,000 cards in a batch, now half of 100,000 is 50,000. Oops, this, I know what I screwed up. This should be 10,000 over, and this one should be 100,000. So half of 100,000 is 50,000, plus 5,000 is 55,000. Divided by 100,000 is going to be 50 cents. I'm sorry, 55 cents per card. All right, and so the bigger the batches are getting, the more efficient my process is, and the less it's going to cost me per card to produce. Now, for part D in that question, if you go back, what is the limit as the x approaches infinity here? Well, in this case, the limit as x approaches infinity of 0.5x plus 5,000 all divided by this value of x. And if you look at this carefully, I don't know what just happened. In this case, the limit is actually going to approach 50 cents per card. All right. And the reason for that is if you break these up, all right, first we're going to divide each term by the value of x. And so this is going to be equal to 0.50 plus 5,000 over x. All right. And so this term goes to 0. And so I'm left with 50 cents per card. Okay, 0.50 cents. All right, so that is example number 3. Now, I'm not sure we did not cover sequences in our discussions of chapter 1 in our textbook. However, I'm hopeful that you are at least somewhat familiar with sequences from your high school math days. All right, because the limits of sequences have many of the same properties as the limits of functions. All right, for example, consider the sequence whose nth term is uh, a to that this should be a to the nth power is 1 over 2 to the nth. All right. So 2 to the 1th is 2, which gives us 1 half. 2 to the, whoops, that should say 1 over 4. Okay. Sorry about that. 1/8, 1/16, 1/32, right? So because 2 to the 1th is 2, 2 to the 2th is 4, 2 to the 3rd is 8, 2 to the 4th is 16, 2 to the 5th is 32. And so as the value of n increases, in other words, as it gets bigger and bigger and bigger, approaches infinity, the terms of the sequence get closer and closer to 0, right? Because the denominator of this fraction is approaching infinity. And therefore, the sequence is said to converge on 0, right, or to 0. And so what we mean by this, at least in limit notation, is that the limit as x approaches positive or negative infinity is 1 over 2 to the nth power equals 0, all right? Of 1 over 2 to the nth power equals 0, okay? And so in this case, the limit as x approaches infinity of f of x equals L, and the limit as x approaches negative infinity of uh, a of n, or a sub n, also equals L. All right, and so that the limit of the sequence is very similar to limits of functions. Okay, so let's have a look at a set of sequences, and we'll do 2 examples of this and see if we can figure out what exactly this means. So in terms of the limits of a sequence, let f be a function of a real variable such that the limit as x approaches infinity of f of x equals L. Well, if a sub n is a sequence, and this should be a sub n, is a sequence such that f of n equals a sub n for every positive integer n, then the limit as n approaches infinity of a sub n is equal to L, a limit, okay? And so we're approaching a limit in either case. Again, as always, the best way to actually look at this is to try an example. So let's do that. All right, for example number 4, you're asked to find the limit of each sequence. And I've given you 3 separate sequences here. And I want you to find the limit of each as the value of n approaches infinity. Now, in this particular case, you're going to do similar things to what we did earlier, but in this particular case, you're going to have a scenario where you're going to have to look at the denominators, and notice that the denominators vary for each of these 3 terms. The numerators are all the same, okay? So for each of these 3 terms, let's actually try to find the limit as n approaches infinity. Okay, so in this case, this is going to be the limit as n approaches infinity. And I'm going to break this up, and I'm going to divide each term by n. And so this is going to be 2 plus 1 over n all over 1 plus 4 over n. Okay? Now, if I take the limit as n approaches infinity of 2, I get 2. If I take the limit as n approaches infinity of 1 over n, I get 0. If I take the limit as n approaches infinity of 1, I get 1. And the limit as n approaches infinity of 4 over n, I get 0 again. And so the limit in this case is 2 over 1, or simply 2. All right? So the limit of as n approaches infinity of a sub n is equal, in this case, is equal to 2. All right, let's try the same thing with the next one. All right, in this case, I'm going to take the limit as n approaches infinity. And in this case, I'm going to divide everything by n squared. And so 2n over n squared is going to give me 2 over n. Excuse me. The limit as n approaches, 1 over n squared is simply 1 over n squared. N squared over n squared is 1, and 4 over n squared is 4 over, is 4 over n squared. Now, what does that mean? Well, the limit as n approaches infinity of 2 over n is 0, right? Because 2 over infinity is 0. The limit as n approaches infinity of 1 over n squared is 0, right? So obviously the numerator is equal to 0. The limit as n approaches infinity of 1 is 1. And the limit as n approaches infinity of 4 over n squared is 0. And so in this case, my fraction simplifies to 0 over 1, or simply 0. All right? And so the limit as n approaches infinity of this sequence, 2 times n plus 1, all over the quantity n squared plus 4, gives me 0. All right. One more. This time we're going to use 4n squared. All right. So I'm going to take the limit as n approaches 0. I'm sorry, n approaches infinity of. Now I'm going to divide everything here by n squared. And so this is going to become 2 over n plus 1 over n squared all over, in this case, 4. Excuse me. Oh, you know what? I messed this example up. I messed this up. This should be 2n squared, which means that this is just 2. Okay? Let's try that again. Sorry about that. So 2 plus 1 over n squared all over 4. Now, the limit as n approaches infinity of 2 is 2. The limit as n approaches infinity of 1 over n squared is 0. And the limit as n approaches infinity of 4 is 4. And so this simplifies to 2/4, which of course simplifies even further to 1/2. Okay, and so that is example number 4. Okay, example number 4. All right. So one more example, and then we'll call it a day. All right. Here, I'm going to ask you to find the limit of the sequence whose nth term is a sub n equals 8 over n to the 3rd times the quantity n times n plus 1 times 2n plus 1 all over 6. All right. Now, if you do a if you do a quick bit of arithmetic here, this becomes, let's see, 8 times n plus 8 times n plus 8, right? No, I lied. It's not. In this case, n squared plus n, let me do this over here. So n times n plus 1 is n squared plus n. And if I multiply that by 2n plus 1, I'm going to get 2n cubed. That's the first. The outer is going to be n squared plus 2n squared plus n. Okay, so 2n, whoops, that's an n, cubed plus 3n squared plus n. Okay, now I'm going to multiply that by 8, and that's going to give me 16n cubed plus 24n squared plus 8n. Okay, now all of that is going to be divided by 6n cubed. All right, 6n cubed, because n cubed times 6 is 6n cubed. Let me do a little bit of quick erasing. Boom, boom. Okay, now back to the pen. Now, in this particular case, if I simplify this a little bit and I divide everything by 2, it becomes 8n cubed plus 12n squared plus 8n, I'm sorry, 4n, all divided by 3n cubed. Now, if I'm going to come back over here to the left side and take the limit as n approaches infinity of 8n cubed plus 12n squared plus 4n all over 3n cubed. Now, in that case, what it's going to be is equal to this. First thing I'm going to do is divide it by, I'm going to divide everything by n cubed. And so this is going to become 8 plus 12 over n plus 4 over n cubed, or squared, all divided by 3. And so the limit as n approaches infinity of 8 is 8. The limit as n approaches infinity of 12 over n is 0. The limit as n approaches infinity of 4 over n squared is 0. And the limit as n approaches infinity of 3 is 3. And so this is going to give me all over 8, rather, all over 3. And so the limit of the sequence that is given here is 8/3. All right, 8/3. Okay. That, my friends, brings us to the end of the second video of, or on section 12.4, the limits at infinity and limits of sequences. And so it's time for me to assign your homework. All right, please do the odd numbered problems at the end of section 12.4, numbers 1 through 37 and 45 through 57. Okay, so that is the end of section 12.4, and I hope you learned something.